Hello everyone, this is Orhan again. In this video, I will be showing you how to run linear regression in Python. First of all, let's import the necessary libraries. These libraries here are from Data Mining for Business Analytics book. It facilitates some of the mechanics. So let's run this and then start loading the data. And now I'm going to import 2020 Roxbury data, which I used in the previous videos. These are Boston house prices. This code drops the missing values. Now I will see the first couple of rows. Now let's see the descriptive statistics of the data. As you can see, we have 3,582 rows, and if you count the columns, you will see that we have 13 variables, one of which is going to be the output variable, which is total value here. Now let's write the list of predictors and the start regression model. So this part is basically the same regression that we did in the previous video, 5b. So I'm going to just like copy it from here and paste it. So you can do the same, or you can just write it again. So basically, we are excluding some categorical variables. We are also excluding the outcome, which is the house prices. And then we are running this. Now I will be writing a code to see the coefficients explicitly. Okay, the first part of the code just prints the intercept and the coefficient. For every variable, we should find the corresponding coefficient. The second part calculates the predictions of y's. So there are two lines here. The first line calculates the predicted values in the validation part, and the second one calculates the y's in the training part. So basically, all of the coefficients you see here are the coefficients of the corresponding variable. For example, when you multiply the land with negative 0.9, gross area with 10.7, etc., all the way down here, and number of parking with 9.9, you will get a prediction for house prices. Basically, these coefficients are obtained from training data set. Now let's see how successful our training is by taking a look at the predictive performance. This can be calculated by two different libraries. The first one is scikit-learn metrics library, and the second one is the MBA library, which is from the Data Mining for Business Analytics books. I will show you both. So let's start with the first one. Okay, in this code, the first line is importing the library. Second line is calculate the mean square error using that library. The third line calculates the root mean square error using the same library. Again, the only difference is I added this term here. This line prints the mean square error rounded to 2 digits, and the last line prints the root mean square error. So let's run the code. We made a tiny little mistake here. Let's rerun again. Okay, so this is the root mean square error. We can calculate the same thing using the DMBA library as follows. As you can see, we obtained the same exact root mean square error here. In addition, this library provides a couple of other metrics too. Now let's do the same thing with validation part. I will be copying and pasting this code, and then I will change the necessary terms from train to valid, which will be validation part terms. As you can see, root mean square is exactly the same here. Basically, I am training my data here, and then my root mean square is $78,000. Using these coefficients, I am predicting in the validation part, which helps me make this much of error. So this is the root mean square error. One question about regression equations is how successful our regressions are. So is there any metrics for that? Well, the answer is yes. There is something called R-square. I again stick to mechanics, but I just give you the idea here. R-square is a number which evaluates the variance explained by the model. So basically, it's the variance explained by the model divided by total variance. It's a number between 0 and 1, or 100%. So the higher the R-square, the higher the predictive power of your model. There are two examples here. The R-square for the regression model on the left is 95%, and for the model to the right is 32%. When the regression model accounts for more of the variance, the data points are closer to the regression line. In practice, you'll never see a regression model with 100%, of course, because in that case, the fitted values equal to the data values, and consequently, all the observations fall exactly on the regression line. But the drawback of a regression line is that the more variables you add your regression, instead of x1, you might add x2, x3, x4, the higher would be the R-square. This is a drawback mainly because you don't want to explain one thing with 1 million variables. So there should be a kind of penalty for adding more and more variables. But basically, R-square shows the power of your regression, but the more variables you add, the higher the R-square. That's why R-square needs a kind of adjustment. Okay, adjusted R-square formula is on your screen, but more important is the intuition. Like R-square, higher values of adjusted R-square indicate better fit. But the thing here is there is a penalty for number of predictors, which is P. When you add more and more predictors, so this formula is kind of penalizing this by increasing the denominator here. That's why when you add more variables, R-square should increase so that it compensates this penalty in the denominator. Other information metrics are Akaike information criteria and Bayesian information criteria. Both information criteria measures the goodness of fit of model, but includes a penalty that's a function of number of parameters in the model. As such, they can be used to compare various models for the same data. All of these three measures helps us to pick the optimal number of predictors in a model. Basically, you don't want to have 1 million predictors in a model. For both of the R-squares, adjusted R-square and normal R-square, the higher the R-square, the better. But for the Akaike and Bayesian information criteria, for these metrics, the lower they are, the better the model. I'm skipping the mechanics of these criteria and how they are calculated, but I'm just trying to give you how they work and what they mean. When we are trying to predict a model, when we are trying to increase or decrease the number of predictors in a model, we have to take a look at those criteria. And then when we add a new variable, the R-square would increase, but how about the adjusted R-square? Similarly, Akaike information criteria and Bayesian information criteria, they should decrease so that we are confident of adding a new variable. So what is the optimal number of predictors in our model? That's the next question. So there are two main methodologies here. The first one is you can start with all predictors and successively eliminate least useful predictors one by one and stop when all remaining predictors have statistically significant contribution by checking the Akaike information and Bayesian information criteria as well as adjusted R-square. So when you eliminate variables, take a look at the adjusted R-square. If it is, take a look at the adjusted R-square and all information AIC and BIC criteria, and then check to see if it's okay to continue or not. The other method is forward elimination. So you can start with no predictors, add one by one, and add new predictors one by one. Again, stop when the addition is not statistically significant by checking adjusted R-square, AIC, and BIC. Now let's see this on Python. Now I will show you how to calculate R-square and adjusted R-square using two different libraries. The first one is going to be called R-square score, and the second one is the MBA library. Okay, let's start with the first one. So as you can see, this model has 89% R square. We can calculate it with the following code too, which mainly derives from the MBA library. As you can see, we calculated the same adjusted R square, 89%, and then additionally we have Akaike information criteria and Bayesian information criteria. So basically, in this model, we are using all of 13 predictors. So if you run a model whose Akaike information criteria is less than 54,547, then that model is basically better than this model. That's what forward selection and backward selection is doing. In all of these models whose R square, adjusted R square, AIC or BICA criteria we calculated are training part of our model. We should also check these metrics in the validation part too. Okay, here you see the actual values of house prices and predicted values of house prices and the difference. So residual is the difference. These are the errors that we make. These all belong to validation part, of course. So we are done with the training part. These are all validations part, and these are the performance of the validation parts, root mean square error of the validation part. Now let's take a look at forward selection models and backward selection models. This model starts with the Akaike information criteria of 54,547. It removes number of parking and checking the Akaike information criteria that decreased by 2, and then removes kitchens again, so it went down by 2, and then remove a square feet and remove number of bedrooms, fireplaces, etc. At some point the code realizes that it cannot go down more, so these are the best variables to predict house prices based on backward elimination. So we can do the same thing with forward elimination, but before that let's check the regression summary of this model with the best variables that we found in backward elimination. So these are the root mean square error of our new model. Now let's take a look at a forward selection model. This model starts with constant model, which means that there is no variable. It's just y is regressed on a constant, and it keeps adding these variables depending on their performance. So it adds gross tax, gross area, etc., and checking again the criteria here, Akaike information criteria. So it was 54,769. It goes down a little to 600 to 500, and all the way down here 54,540 is the ultimate Akaike information criteria that the model obtained, and the model decides that these are the best variables. Now let's check if they are the same here. Both models came up with the same predictors as best predictors. Now lastly, let's print out all of the information that belongs to this regression. This is the last output in this class. Basically, this is a regression result which encompasses everything that we discussed up to now. So here you see all the variables and their coefficients. And then here in this column, you see if they are statistically significant. So the computer is always checking the statistical significance, meant it's just like removing one variable. For example, if you start with all of these 13 variables, the first variable you start with removing might be number of parking, but it's the least insignificant one here. And then you see R square here, you see adjust R square here, Akaike information criteria, Bayesian information criteria, they are all summarized here. In this video, I showed you how to run regression with train test split model in Python. Basically, we divide the data into two pieces, training data and test data or validation data. So we train the data in the first half of the model. Checking the performance of the model, we run the prediction in the validation part. On your screen, you see regression output of training part of the data. Well, I hope you enjoyed this video. Hope to see you in the next videos.